We have a great lineup of speakers. The first one, the Dr. Anatoly Frenkel, who is from Brook National Lab and Stony Brook University. I would like him to kickstart.
Thank you. Thank you very much. Thank you to the organizers for this very interesting workshop and for inviting me. And I'll start by telling you that in our group, we are very interested in finding the functional units in nanostructures. And this means not just units, active species in catalysts, but it also includes other materials, other functional materials that have their explanation at the local structure at the nanoscale. And for us, it's interesting to learn how to find that link, how to find the explanations of the activity of different materials, different devices, by finding that structural units. And that ranges from, of course, active sites and active species in catalysts, but not only. We also look for details of structure in quantum dots, explaining why they absorb or emit light at certain wavelengths, linking that to the structure of dopants and the methods of incorporation of dopants in the lattice. We also investigate other materials, electromechanical, for example, where local details of dopants in ceramics may explain why they can generate large mechanical stress in response to electric field and so on. So the list goes on, and the question is the same theme. What is the structural mystery that holds the key to this activity? And it's actually difficult to answer because in the nanoscale, we are lacking experimental techniques that give this answer with a sufficient precision. So we cannot use the method proposed by Francis Crick if you want to understand function, study structure, because the structure itself is very elusive, difficult to understand. So our approach, and I will tell you what it is, how to obtain the information about these functional units. But first, suppose we have that information, what do we do with that? How do we link it to activity? Until I heard the talk by Mark Porosov, I thought that there are only two prevalent methods, either by starting with atomic coordinates or by using descriptors. But now we know we can ask ChatGPT and it will give the answer why materials function. But besides that, we still want to understand what's the explanation at the level of physics. And for that, we need to have descriptors. We can't have atomic coordinates. We need to have descriptors. And what people do with these descriptors, one example is from the older work by Jim Carruthers from Purdue. I think it's one of the first where descriptors were used to understand mechanisms of chemical reactions. And here, there is a link on the left graph between the model of catalysts interpreted in terms of those descriptors and the observed reaction rates. And to make the link, the descriptors were used as input in kinetic equations, and they were used to explain performance. And conversely, by starting with performance and back propagating this information to the catalyst formulation, they proposed that how can we do the design, inverse design. In the work, which is probably among the first in which artificial neural network was used for catalysis modeling, well before our time, 95, and I didn't know about that work until recently. Hattori and Kito proposed to use descriptors and completely bypass kinetic models and mechanisms by directly linking or mapping them on the performance. And in this case, the descriptors were some quantities describing charge, interatomic distances, coordination numbers, and such. And the functionality was described in terms of conventional parameters describing catalytic selectivity. In this case, it was oxidative dehydrogenation of ethyl benzene. And the challenges are in the lack of those descriptors that can be provided by experiment. And in some cases, they can be, but in unfortunate field that I'm working in, where we investigate very dispersed, very small catalytic structures, we don't have that information available to us. So we need to find a way to provide these quantities to theorists, to try to make our own sort of simple man investigation, how we can link the descriptors and performance. Without theory, either way, we need to understand the descriptors. And what we propose to do, instead of finding the structure for understanding function, we propose to investigate spectra. Spectra is the experimental data, and those come across together with diffraction patterns, images, something that communicates the information about the structure, but it's not structure. So in our case, we are using spectra to invert them, to map them on the descriptors, and hopefully closing the loop. We also are interested to know how much information is in the spectra, because according to this list, the choice of descriptors is completely unbound. It's really in the eyes of the beholder. People can use ones or the others, and it's still not very clear what to use, but it's also not clear how many descriptors are hidden or encoded in experimental data and how to decode them from the data. So that's also something that we're working on. And of course, this is not a realistic path for understanding working catalysts unless we solve the problem that was already highlighted in earlier discussion, how to separate catalysts working in which they coexist with spectators, and they may coexist with different forms of catalytic metals, reduced or oxidized in different sizes. And these fractions or speciations may change in reaction conditions. So that also comes as a prerequisite that if you know only when this speciation is done, and we can isolate the catalytic species, we can analyze their spectra, we can provide this to people like Boris Kovinsky, who can model them using machine learning force fields and predict catalytic activity and explain mechanisms. And I mentioned Boris only as an example. So, so these are the general fields that we're working in. I'm only going to talk about the first three, but I'll briefly mention that we have a active effort in dealing with the last two. So how to prepare this work for analysis, how to zoom in on active species to understand their spectra. We need to be able to separate multiple species by using either multimodal operando characterization, using this method shown here, where we have coexistence of different species. We combine techniques either in one instrument or using a portable reactor, taking it from one experiment to another. And by doing that, we have access to spectra coming from independent different species. We know how many they are and what each spectrum looks like. But the advantage is that it will be a spectrum of a given species, and we can improve the purity of the data by doing that. That is more or less interparticle heterogeneity, what I just described, where you have heterogeneity in a way that different particles have different composition, sizes, and degree of oxidation. But this heterogeneity may exist even in the same particle. By that, I mean that the surface species may be very different from the bulk, and this is intraparticle heterogeneity. And catalysis occurs on the surface. It's a cliche, but how do you extract the information from the surface? There are methods we use, such as modulation excitation spectroscopy, that gives us signal coming predominantly from the catalytic surfaces. And this information can be further improved by using high energy resolution methods, such as those available at synchrotron sources. And that simply improves sensitivity to these features. They give us spectra with a better spectral signatures, better resolution. And finally, more futuristic, but doable, at least in one capacity methodology, is by actually going to single nanoparticle and trying to get spectra from a particle. And that can be done either by using future capabilities of X-ray sources with a fine beam size, or already in present using capabilities of electron microscopy. And electron energy loss spectroscopy can be done by using Zane's-like spectra or EEL spectra from single particle and measuring spectra from a single catalyst. In principle, it's possible. But once we have the spectra, what do we do with them? So this is the whole big chunk of activity in our group, is by trying to map the spectra on the descriptors. This is an example made by, I think, in response to an inquiry to DALI, to draw a machine that would take spectrum as an input, XOFs in this case, and produce some descriptors as an output. And that's like a logo of our group, at least a part of it, which does machine learning. So what is the essence of this approach is that you have this spectrum that in our case, it's XAFs or XANES. It can be EELs, it can be probably other spectroscopy data that have this connection to the structure on one hand, and they can be used to create training sets on the other hand. Only in that case, we can use supervised machine learning to map spectrum on the structure, and XANES works just fine for that. So once you have this neural network, you can use it as a magic wand to pull out all these descriptors from the head, or so we think. Why not to use conventional XAFs, which is traditionally used for getting descriptors such as coordination number and distances? Well, we find that in the limit of nanostructures operating in real environment at high temperature, dilute compositions, XAFs does not give sufficient sensitivity, signal to noise ratio is poor. Plus, all the limitations in the technique come to the fore that it's not good for disordered non-Gaussian distributions of bonds, and any attempt to use conventional analysis fails because the prediction of coordination numbers will be wrong, and distances and disorder parameters. And people who work with molecular dynamic XAFs model and know, and this is the reason why they use them, because conventional analysis of XAFs would not work. So instead of XAFs, a good alternative is to use XANES. In fact, we don't have really too many other options, because if data quality is poor in XAFs, the only chance that we will have something useful is the near edge region, because it has pretty good intensity, better quality than XAFs. But the information in XANES is essentially the same as in XAFs, except it's more like a black box. It cannot be fit. There is no equation that you can use to fit XANES and get adjustable parameters from the fit. But you can go in the forward direction. You can start from the structure, and you can model theoretically X-ray absorption spectra. The modeling programs are very advanced for this purpose. You cannot go backward. You cannot extract structural coordinates from the spectra, but we are not too stressed out because of that, because what we are doing is we're mapping directly the spectra on the descriptors. Descriptors also can be directly obtained from the structure, but not back. But again, in our approach, the idea is that we are decoding the spectra to obtain descriptors, and there are several advantages of doing that. One is that we still get structural information in absence of XAFs. Second, we can get much more from the spectra than we can do by conventional fitting of XAFs. And the reason is that both spectra and structural descriptors, such as shape, coordination numbers are the workhorse descriptors in catalysis, but not only coordination numbers can be extracted. For example, pair distribution function, generalized coordination numbers, which have the meaning of the environment, not only the first neighbor, but what is this first neighbor has in its surrounding as well. So all of this can be mapped or correlated with the spectra, and we learned how to decode this information. So one possibility is to use an artificial neural network to have spectrum as an input and the descriptors on the output. And those descriptors may be directly what we're looking for. For example, the oblateness of the nanoparticle or generalized coordination number, or it can be something more abstract, such as surface to volume ratio. And then using other strategies such as genetic algorithm, we can find the correlation between those descriptors and already useful parameters such as shape. So I'll walk you through very briefly, because still have a little time for that. To go in one direction from structure to descriptors, it's trivial, because once you have coordinates, you can calculate all these descriptors, which are dependent on atomic coordinates of each atom. And then that can be arranged as shown here from the nanoparticle shapes or structures. You can get coordination numbers from some polyoxymethylates. You can get pair distribution function. This is trivial. In terms of this direction, as I already mentioned, there are very robust codes based on solving the equation relating absorption coefficient and transition rate of electrons under electric field. And FEF, for example, is one code, FDMS is the other, and they use real space green function calculations to solve this golden Fermi golden rule. equation and find theoretical formula, theoretical data for absorption coefficient. That can be done for any input. And we take advantage of that by modeling single atoms, nanoparticles, bimetallics, clusters, and so on. And the idea is that you combine different absorbing atoms, as shown in the bottom right, for example, to generate theoretical spectrum of the nanoparticle. This is how experiment is done. So we're mimicking this process. And by sending the input into the neural network that is trained using this theoretical training set, we are able to identify anything on the output, anything that is related to the same structure for training. So by doing this, we managed to analyze structures of very different catalytic species, ranging from single atoms to clusters, I already mentioned. But also we can analyze those structures which are not available for traditional XAFs analysis, such as those containing elements which are neighbors in periodic table. XAFs would not be having sufficient resolution, spectral resolution, but XANEs can do that because the sensitivities to the charge transfer between different neighbors, and that affects the XANEs features. So we can do it using neural networks. And the autoencoders are very useful for this purpose because the latent space in the autoencoder tells us what is the minimum amount of information that is needed to reconstruct the spectrum. So by using the number of nodes in the latent space as a variable, and by changing the number so that the reconstruction will be adequate, we know what's the minimum number of nodes in the latent space to reconstruct the spectrum. And that gives us the limit of how many descriptors we can extract from the spectrum. Without that, it would be impossible to know what amount of information is in the XANEs, because the Nyquist criterion would not work for XANEs. It's only working for XOR. So this is the summary slide. On the left is the approach that we use, and this QR code shows a number of papers that we published on different applications. And I think we have conceptual understanding that it works. In many cases, we tried. There's still a lot of work to do. We are only in the beginning of mapping the spectrum on useful quantities, size, shape, morphology of nanoparticles directly. We still are in the beginning of learning how to use machine learning for speciation, classification, and regression for solving heterogeneous species. The idea that we have here is that we use classification after we perform experimental separation of species using, for example, principal component analysis, where we have changing fraction of different species in real reaction. Once we get the spectra of each species, we use classification to basically attribute it to certain complex, and then we use regression to understand the descriptors. So this is the approach we currently use, but maybe there are others. We think that this can be this is a very fast method, by the way, because neural network, after it's trained, can produce these results pretty much instantly. So we think that using it as a data pipeline can be another future application of this method, where imagine that you run an experiment and your catalyst deactivates and you want to know why. And with neural network, not only you will know why, for example, the size or shape of the particle changes, but you can also give a feedback information back to the reactor to offset that effect. So this is where we are now. Thank you for your attention.
Any questions?
Frank, really nice talk. I like the approach, but I have a question, or maybe I don't understand this or exactly that much. So let's say when we have the heterogeneous pairs, they can be different size combined together in one sample. Then when you do the Zinso exams, that is kind of like an ensemble effect of those different size of the nanoparticle together. But when you do the model, you fit one nanoparticle, maybe they coincidentally map each other. Then how you kind of like distinguish, maybe it's kind of like two wrong factor together to get the same spectrum instead of really.
This is a beautiful question. I'm sorry I did not fully address it, but I was trying to. It's an ill-posed problem. If you have a distribution of species in your spectrum and you have only one spectrum, it's a completely degenerate problem. You cannot represent, first of all, number one, it cannot be used to represent any, typical species in the sample, because it may be no such species. Because if you have bimodal distribution, the average will be something that doesn't exist. If you have 40%, 60% in one group, 60%, 40% in the other, the average will be 50-50, but there is no such catalyst. So we're very careful not to do that. In order to apply this approach, first we need to perform speciation. So by speciation, I mean use experimental methods to isolate spectra coming from individual species. This can be done by using linear algebra methods, principal component analysis, and others. This is what people routinely use. Once you have a spectrum of pure species, then you can apply this method. So we recognize that.
Brook comes set up. You can take one more question. Yeah, Johannes.
Hi, thank you.
Hi.
I think it's super cool work with machine learning to convert from sayings to structure. So I think a lot there is you recover rate distribution functions. How feasible is it to get any, like, as Boris mentioned this morning, how important it is to get direction information, or does that work too?
Good question. The distribution functions we can recover not from Zanes, from XOFs by using a similar approach. But directional information is not available in XOFs. It collapses everything in one-dimensional function. In Zanes, probably some bonding angles can be studied, but we didn't try. Okay. Thank you.
All right. Well, thank our speaker one more time.